The Messerschmitt Me 262 marked a decisive shift in military aviation during the final phase of the Second World War. Entering operational service in 1944, it became the world's first mass-produced jet-powered fighter aircraft. This documentary focuses specifically on the Me 262A1A Schwalbe, the standard single-seat fighter variant. Using technical records, pilot manuals, and production data, this analysis examines the aircraft's design, systems, and operational employment in a strictly historical and engineering-based framework. Airframe. The Messerschmitt Me 262 employed a low-wing twin-engine monoplane configuration, optimized for high-speed jet flight. The aircraft featured two turbojet engines mounted in streamlined nacelles beneath the wings, reducing asymmetric thrust risks and simplifying structural integration. This configuration also allowed a slimmer fuselage, lowering frontal drag while preserving internal volume for fuel, armament, and systems. The Me 262 A1A measured approximately 34 feet 9 inches in length, or 10.6 meters. Its wingspan was about 41 feet, or 12.6 meters, while overall height stood near 12 feet 6 inches, or 3.8 meters. The fuselage had a circular to oval cross-section, chosen to better distribute structural loads and reduce stress concentrations at high speed. The nose section was blunt to accommodate heavy forward-mounted cannon, while the fuselage tapered gradually toward the tail to reduce pressure drag. Structural design philosophy was dictated by wartime limitations rather than ideal engineering margins. Designers prioritized simplified production, reduced material usage, and rapid assembly over long-term airframe life. The aircraft was expected to serve a short operational lifespan under combat conditions. Aerodynamic efficiency was pursued where practical, but compromises were accepted to reduce tooling complexity and manufacturing time. Material selection reflected severe strategic shortages. Aluminum alloys were reserved for primary load-bearing structures such as wing spars and fuselage frames. Steel was used extensively in high-temperature areas, particularly around engine mounts and exhaust sections. Plywood and other non-strategic materials were applied to access panels, fairings, and internal components to conserve critical metals while maintaining acceptable strength. Internally, the fuselage followed semi-monocoque construction principles. Longitudinal longerons carried primary bending loads, while frames and formers preserved fuselage shape and distributed stress. Stringers supported the thin external skin, allowing it to contribute structurally without excessive weight. This arrangement provided sufficient rigidity for sustained flight near 540 miles per hour or 870 kilometers per hour. Manufacturing realities strongly influenced final airframe quality. Production was dispersed across multiple factories, including underground sites, to mitigate Allied bombing. Skilled labor shortages led to reliance on semi-trained workers, producing inconsistent tolerances and surface finishes. These variations affected aerodynamic efficiency and handling characteristics across individual aircraft in operational service. Bulkheads and fuselage skin. The Me 262 fuselage incorporated multiple bulkheads to compartmentalize fuel, armament, and cockpit areas. A forward bulkhead separated the ammunition storage from the forward fuel tank, while another divided the forward tank from the cockpit. A third bulkhead was positioned aft of the cockpit, isolating the rear fuel tank, and an additional smaller bulkhead protected the gun camera compartment. Each bulkhead maintained structural integrity, while providing fireproofing where proximity to ammunition or fuel created risk. Critical bulkheads adjacent to ammunition and fuel tanks were reinforced with steel and fireproof materials to prevent propagation of fires or explosions. Secondary bulkheads utilized aluminum with stiffeners and open cutouts for routing cables, fuel lines, and control linkages, ensuring that operational systems remained functional without compromising structural strength. This design allowed the aircraft to retain integrity even when some compartments were damaged. The external fuselage skin was composed primarily of duralumin sheets 2 mm or 1/16 of an inch thick. Sections surrounding the forward gun barrels were fitted with steel plates to withstand muzzle blast and heat. Each skin panel was riveted to the internal longerons and stringers, ensuring load transfer between the skin and the frame. After assembly, all seams, holes, and access panels were carefully finished with fillers or doped fabric to smooth irregularities. The surface was then polished and painted to reduce aerodynamic drag, improving high-speed performance. These techniques minimized airflow turbulence along the fuselage, ensuring the Me 262 could maintain velocities up to 540 miles per hour or 870 kilometers per hour without excessive skin friction losses. Routed conduits and attachment points for control linkages were carefully integrated, allowing maintenance personnel access while keeping aerodynamic contours intact. The combination of reinforced bulkheads, precision skin fitting, and finishing treatments reflected a balance of structural safety, operational functionality, and aerodynamic efficiency critical for early jet combat operations. Wings. The Me 262 featured a double-spar wing design, providing both structural rigidity and load distribution across the span. The main spar was fabricated from steel, supporting the primary aerodynamic and weight loads, while the auxiliary spar was constructed from duralumin to reduce overall weight. Both spars were connected by main ribs and auxiliary ribs, forming a lattice framework that maintained wing shape under aerodynamic forces. Wing skins were primarily duralumin sheets, 2 to 2.1 millimeters thick, or approximately 2/25 of an inch. On the lower surfaces, thin steel sections of 0.25 millimeters or 1/10 of an inch reinforced areas subject to higher stress or heat exposure. This combination of metals balanced durability, weight, and manufacturing feasibility under wartime resource constraints. The wingspan measured 41 feet 4 inches, or 12.6 meters, with a leading-edge sweep angle of 17 degrees. The transverse angle, which is the tilt relative to the aircraft's horizontal axis, was set at 5 degrees, giving the wings a slight upward dihedral. This configuration improved lateral stability and roll response during high-speed flight and maneuvering. Along the leading edges, retractable 3-section slotted automatic wind slats were installed, except where engine nacelles occupied space. These slats deployed at high angles of attack, enhancing lift during slow-speed maneuvers, takeoffs, and landings. By improving airflow attachment to the wing surface, they reduced the risk of stalling at lower airspeeds. Trailing edge flaps extended the wing area when deployed, generating additional lift during takeoff and landing phases. On the Me 262, the flaps were interlocked with the landing gear system, allowing deployment only when the undercarriage was lowered. This safety logic prevented accidental high-speed flap extension, which could result in structural stress or aerodynamic disruption. The flaps were two-sectional and separated by the engine nacelles, maintaining balanced lift distribution across the span. Ailerons controlled roll and were also divided into 2 sections to mitigate aerodynamic deformation effects. Each section responded independently to control inputs, ensuring precise roll control at high speeds. This separation also reduced the risk of structural twisting under high aerodynamic loads, which was critical given the jet's unprecedented velocity range for the era. The combination of a double spar framework, mixed metal skinning, sweep angles, automatic slats, and separated control surfaces allowed the Me 262 wings to deliver both aerodynamic efficiency and operational reliability. These design choices were fundamental to achieving high-speed performance, maneuverability, and safety during the aircraft's brief but intensive operational deployment in World War II. Tail section. The Me 2062's tail assembly consisted of a vertical stabilizer and rudder, along with a horizontal stabilizer and elevators. The vertical stabilizer provided directional stability, while the rudder controlled yaw, allowing the aircraft to turn left or right along its vertical axis. The horizontal stabilizer maintained longitudinal stability, and the elevators controlled pitch, enabling the aircraft to climb or descend. Both surfaces were constructed entirely of metal, matching the structural integrity and durability of the wings. The horizontal stabilizer featured a sweep angle of 23 degrees, and the vertical stabilizer had a sweep angle of 45 degrees. These swept configurations reduced aerodynamic drag at high speeds and contributed to stability during rapid maneuvers. Construction materials included duralumin for primary structural elements and steel in high-stress areas, ensuring strength while minimizing weight. The tail design mirrored the wing's swept-back style, maintaining consistency in aerodynamic characteristics and flight behavior. Overall, the tail section balanced stability, control, and structural efficiency, allowing pilots to safely handle the high-speed and high-performance characteristics of the Me 2062 jet fighter. Landing gear. The Me 2062 featured a tricycle landing gear configuration, with a single nose wheel at the front and 2 main wheels located under the wings. This arrangement provided improved ground stability and better control during taxiing, takeoff, and landing compared to conventional tail dragger designs. Each main wheel was equipped with an oil pneumatic shock absorption system, allowing it to absorb landing impact forces and reduce stress on the airframe. The nose wheel also incorporated a similar suspension mechanism to handle rough or uneven surfaces. The landing gear was extended and retracted using a hydraulic system powered by the aircraft's onboard hydraulic pumps. The mechanism allowed smooth and reliable deployment, while ensuring the wheels were securely locked in position during flight. This design provided safe ground handling, minimized landing stress, and supported the operational requirements of high-speed jet operations. Engines. The Me 262 was powered by 2 Junkers Jumo 004B1 turbojet engines, which represented the first operational axial-flow jet engines in military aviation. Each engine produced a thrust of 8.83 kilonewtons, 1,984 pounds force, enabling the Me 262 to achieve unprecedented speeds for its time. The Jumo 004's development marked a significant milestone, influencing the design of all subsequent turbine engines. Air was drawn into the engine through the open inlet and passed into an 8-stage axial compressor. The compressor increased the air pressure before directing it into 6 individual combustion chambers. Within each chamber, fuel was injected and ignited, producing a high-velocity stream of exhaust gases. Part of the energy from these gases powered the axial compressor, while the remainder exited the nozzle to generate forward thrust. The exhaust flow was managed by a movable inner cone known as the Zwiebel, or onion bulb, which controlled the expansion of gases and allowed pilots to optimize engine performance under varying flight conditions. This feature was critical for maintaining stable thrust during acceleration and climb. Each Jumo 004 engine measured 12 feet 8 inches 3.86 meters in length and 2 feet 8 inches 81 centimeters in diameter. The weight was approximately 1,585 pounds, 719 kilograms, a significant consideration for aircraft balance and center of gravity. To start the engines, a 2-cylinder 2-stroke gasoline-powered Riedel starter motor was employed. The starter rotated the turbines to initiate airflow, after which the pilot engaged the ignition system to begin combustion. The Jumo 004 was designed to operate on multiple fuel types, including the German WW2 synthetic fuel J2, derived from brown coal, and even diesel in emergencies. This flexibility was essential given wartime fuel shortages and logistical constraints. With both engines running at optimal power, the Me 262 achieved a maximum level flight speed of 540 miles per hour, 870 kilometers per hour. In a dive, the aircraft could exceed these speeds, although pilots were cautioned to avoid exceeding approximately 560 miles per hour, 900 kilometers per hour, to prevent structural stress. During early transonic testing, prototype aircraft reached speeds over 970 kilometers per hour, resulting in severe vibrations and temporary loss of control. These early transonic effects required strict pilot adherence to recommended speed limits to maintain safety. The twin Jumo 004 engines enabled an exceptional rate of climb of approximately 20 meters per second, 67 feet per second. However, operational dive rates were less remarkable compared to late-war Allied fighters, prompting German pilots to approach bomber formations cautiously to avoid exceeding safe speed thresholds. The engine's performance demonstrated both the potential and limitations of early jet propulsion, providing unmatched speed while presenting unique handling challenges at high velocities. The integration of the Jumo 004 B1 engines into the Met 26-2 airframe exemplified the first successful application of axial-flow turbojets in combat aircraft, setting the standard for post-war jet design and influencing future military and civilian aviation development. Fuel system. The Me 262 featured a dual-tank fuel system, comprising 2 main rubber self-sealing tanks, each with a capacity of 238 gallons, 900 liters, and supplementary auxiliary tanks providing an additional 204 gallons, 770 liters. The main tanks were located within the fuselage, positioned to maintain balance and center of gravity, while the auxiliary tanks were installed to extend operational endurance. Fuel delivery to the engines was controlled by the pilot through a cockpit switch, allowing either engine to draw from the right or left main tank as required. This system provided operational flexibility but required careful attention to maintain fuel balance during flight, ensuring stability and proper weight distribution. A warning light in the cockpit alerted the pilot when fuel levels dropped to 250 liters 66 gallons, signaling the need for careful monitoring. Pilots were responsible for actively managing the fuel selector valves and monitoring consumption rates to prevent imbalance or engine starvation. At maximum capacity, the combined fuel volume allowed the Me 262 to remain airborne for approximately 60 to 90 minutes depending on throttle settings and flight profile. This endurance translated into a maximum theoretical range of 1,050 kilometers 65. The fuel system's design emphasized operational reliability, redundancy, and pilot awareness, integrating self-sealing construction and flexible engine feed controls to optimize safety and performance under wartime conditions. Armament. The Me 262A1A was armed with 4 Rheinmetall-Borsig Mk108 automatic cannons mounted in the forward nose section. This centralized nose installation eliminated the need for gun convergence at a specific distance and allowed all weapons to fire directly along the aircraft's longitudinal axis. The placement maximized accuracy during high-speed firing passes and simplified aiming during brief attack windows against enemy aircraft. Each Mk108 had a caliber of 30 mm or 1.18 inches and operated with a cyclic rate of approximately 600 to 650 rounds per minute. The muzzle velocity was relatively low at about 540 meters per second or 1,770 feet per second compared to Allied fighter cannons. This lower velocity reduced effective firing range but was compensated by the weapon's heavy explosive payload. Ammunition supply was stored in drum magazines located directly behind each cannon. Each gun was provided with approximately 100 rounds, giving a total onboard ammunition load of roughly 400 rounds. The short ammunition belts and direct feed paths reduced the risk of jamming and allowed reliable operation during high-speed maneuvering. Spent casings were ejected downward through ports in the fuselage to prevent interference with the engines. The Mk-108's ballistic effectiveness was optimized for bomber interception. Each high-explosive shell contained a thin casing and a large explosive charge, designed to detonate inside aircraft structures. A single hit was often sufficient to destroy heavy bombers such as the B-17 or B-24 by rupturing spars, fuel tanks, or control systems. Against smaller, more agile fighters, the low muzzle velocity required pilots to close to very short ranges, typically under 200 meters or 656 feet. The cannons were rigidly mounted to the aircraft's structure without synchronization mechanisms, as there was no propeller arc to consider. This mounting improved mechanical reliability and ensured consistent recoil forces, reducing vibration and dispersion during firing. A reflector gun sight assisted aiming, calibrated for short-range, high-speed attacks typical of jet interception tactics. A gun camera was installed above the nose armament to record firing sequences and confirm combat claims. The camera was electrically triggered with the cannons, providing visual documentation for mission analysis and pilot debriefing. This system also aided training and tactical refinement. In later operational use, the Me-262 was additionally equipped with R-4M air-to-air rockets mounted on wooden launch rails beneath the wings. Each aircraft could carry up to 24 rockets, fired in salvos to saturate bomber formations. The R-4M had an effective range of approximately 1,200 meters, or 3,937 feet, allowing attacks from beyond defensive gunfire. While accuracy depended heavily on pilot alignment, the rocket system significantly increased the aircraft's bomber-killing capability.
Cockpit. The cockpit of the Me-262A1A was designed to provide essential protection and functional efficiency within the constraints of wartime production. The pilot was protected at the front by a bullet-resistant armored glass panel approximately 90 millimeters or 3.5 inches thick. Behind the seat, a steel armor plate measuring about 15 millimeters or 0.6 inches shielded the pilot from rearward fire. Later aircraft extended this armor upward to protect the head and neck. The canopy was a three-piece design, offering adequate forward and lateral visibility while maintaining structural simplicity. The overall layout philosophy followed established Luftwaffe practice, prioritizing familiarity for pilots transitioning from piston-engine fighters. Controls were arranged to minimize pilot workload during high-speed operations. The seat lacked padding, requiring the pilot to sit directly on the packed parachute, which simplified construction and reduced weight. The instrument panel was divided into two primary sections. Flight instruments, including airspeed, altitude, and attitude indicators, were grouped on the left side to support basic aircraft control. Engine instruments, such as exhaust temperature, RPM, and fuel flow indicators, were concentrated on the right, reflecting the increased monitoring demands of early jet engines. Engine throttles, trim controls, and fuel selectors were located on the left side console, allowing fine power adjustments with the pilot's left hand. Electrical systems, radio controls, and engine starter mechanisms were positioned on the right side panel. This separation reduced control congestion and improved task organization. The primary gun sight was the Revi-16B reflector sight, projecting a fixed reticle onto a glass combiner. While reliable, it lacked gyroscopic lead computation, limiting effectiveness against maneuvering targets and requiring pilots to rely heavily on experience and judgment.
Startup procedure. Pilot entry into the Me-262 was accomplished by climbing onto the left wing and opening the center section of the canopy upward. After stepping into the cockpit, the pilot seated himself on the parachute and secured the harness. This arrangement reduced seat complexity and allowed rapid egress if necessary. The startup sequence followed a strict order to prevent engine damage. The pilot first activated the battery switch, followed by the inverter and electrical generators. Fuel selector valves were confirmed closed, and engine throttles were set to minimum to avoid uncontrolled acceleration during ignition. Engine priming was initiated using the Riedel two-cylinder, two-stroke gasoline-powered starter motor mounted within each engine nacelle. The pilot engaged the starter handle to spin the compressor and monitored the tachometer. When rotational speed reached approximately 700 to 800 revolutions per minute, ignition was activated. At ignition, fuel was introduced into the combustion chambers, producing a distinct pulsing sound as combustion stabilized. Engine speed was then carefully increased to around 1,800 to 2,000 RPM. At this stage, the engine became self-sustaining, allowing the starter system to be disengaged. Once stabilized, the pilot gradually advanced the throttle to approximately 3,000 RPM. Initially, fuel was supplied from the rear tank to both engines. As engine temperatures and RPM stabilized, fuel feed was switched so that each engine drew from a separate main tank to balance weight. During ground operations, directional control was maintained using differential braking on the main wheels, as the nose wheel was not steerable. Careful throttle application was essential, as rapid power changes could lead to compressor stall or flameout.
Takeoff. Taxiing the Me-262 required cautious throttle input and precise brake control due to limited low-speed maneuverability. Directional control on the runway was maintained using differential braking, as aerodynamic control surfaces were ineffective at low speeds. For takeoff, the control stick was held in a neutral position. Throttles were advanced slowly to avoid engine surge while allowing both engines to reach stable high power settings. Acceleration was gradual compared to piston fighters. At approximately 200 km per hour or 125 miles per hour, the pilot applied gentle back pressure on the control stick. This raised the elevators and allowed the aircraft to lift off smoothly. Brakes were briefly applied to stop wheel rotation before retracting the landing gear, reducing mechanical stress on the system. Combat flight operations. After takeoff, the Me-262 typically climbed above the anticipated altitude of enemy bomber formations. This initial climb strategy preserved energy and allowed the aircraft to attack from a position of advantage. Once in the patrol area, weapon systems were powered and armed. Interception positioning emphasized speed and altitude rather than maneuvering. Pilots approached from the side and above enemy formations to minimize exposure to defensive fire. Attacks were conducted in shallow dives to convert altitude into speed while maintaining control. Attack geometry focused on high-speed slashing passes through bomber formations. Pilots aimed to cross the formation laterally, firing at short range to maximize the effectiveness of the 30mm cannons. Rocket salvos were typically launched from greater distances to disrupt formations before closing for gunfire. Gunnery required precise timing due to limited firing windows. Short bursts were used to conserve ammunition and reduce recoil effects. Rockets were often fired in volleys to compensate for limited accuracy. After the attack, the Me-262 used its superior speed to disengage. If threatened by escort fighters, pilots relied on straight-line acceleration rather than turning combat. This energy-based tactic allowed the aircraft to exit combat zones rapidly and return to base. Vulnerabilities. Rat catching. Despite its speed advantage, the Me-262 was vulnerable during takeoff and landing due to slow acceleration and limited low-speed maneuverability. Allied fighters exploited these phases by patrolling near known jet airfields. This tactic, known as rat catching, involved diving attacks on aircraft as they approached or departed runways. The Me-262's engines responded slowly to throttle changes, limiting evasive options at low altitude. Operationally, this vulnerability forced the Luftwaffe to allocate fighter escorts and anti-aircraft defenses around jet bases, reducing overall effectiveness and complicating deployment. Summary and legacy. Approximately 1,400 to 1,500 Me-262 aircraft were produced, but only a fraction became operational due to fuel shortages, pilot training limitations, and logistical disruptions. Fewer than 300 aircraft saw sustained combat use. Strategically, the Me-262 arrived too late, and in insufficient numbers to alter the outcome of the air war. Industrial damage and Allied numerical superiority constrained its impact despite technical superiority. Nevertheless, the aircraft exerted significant influence on post-war aviation. Its underwing engine nacelle configuration, swept-wing concepts, and axial-flow turbojet architecture informed the design of later aircraft such as the MiG-115 and F-86. The Me-262 demonstrated both the promise and challenges of early jet propulsion. Its legacy lies not in battlefield success, but in establishing the foundational principles of modern jet fighter design.